So I think I can probably finish spectral sequences today. Let's just hope that, me being late and all, hopefully that doesn't impede that, but we'll try. Okay, so last time I just want to summarize basically. Well, okay, maybe we can just look at the two here. So we can start with a double complex and we can filter the total complex in two different ways. The first way is by columns, and so that's by taking the total complex of sort of the chopped up version of the total of the double complex. So we can sort of just look at everything to the right of a certain column and take its total complex, and that gives us the gives us a filtration by columns. And then there's a corresponding spectral sequence that we get. And it's in some shape that I described last time, or in some maps and some modules. And then the second way is to do it by rows, which is you start at a fixed row and you look at everything above it in the double complex. You replace everything below by zeros, take the total complex of that, and that gives you each of the pieces of the filtration. And of course, you get another spectral sequence. It looks a little different. The maps are slightly more confusing, just because now the rows have become the columns in the spectral sequence, so everything has been reflected. So now the differentials, at least at the 0th page. Is this 0? Yeah. At the 0th page are the horizontal differentials from the double complex, but they appear vertically in the spectral sequence. So it's a little weird, but yeah. Okay. So here's one application, and you'll have to forgive me. This is it actually does not use the co-homological version of everything that I've been speaking about. It uses the homological version. So I'm going to report this result, and you can, it's a good exercise to sort of reinvent everything that I've talked about, but for the homological spectral sequence version, and then try to carefully prove this theorem. So here's the application, which is balancing Tor, which is to say that you can left derive two different tensor products to get the same Tor groups. So Ln a tensor dash on B is isomorphic to, I'm going to call this smiley face, Ln dash tensor B. Oh, am I recording? I hope I am. I think I am. Yeah. On A. And so why is this? I'll give you a skeleton of a proof. So you use projective resolutions of either A or B, right? So we have projective resolutions, oh dear, resolutions, P going into A or Q going into B. And so there are two homological spectral sequences converging to the homology of the total complex. So spectral, so homological. So, okay, so two homological spectral sequences converging to the homology of now tote P tensor Q. And so, what is this double complex P tensor Q? It's what you think it is. It's at every PQ, you just take P sub P and Q sub Q, and you tensor them together, and you form a grid. This grid is going to be concentrated. It should be in the upper half plane, right? Maybe Okay, don't worry about it. It doesn't matter that much. But it's a double complex. And it's nice enough that you can actually calculate things explicitly with it. Okay. So, right, there are two of them, so I'll just detail them both in each column. So since the vertical homology of, now if I look at P sub P tensor Q, so this is now just, I'm looking at one column, the Pth column, and I'm looking at the Q homology there. This thing is equal to P sub P tensor HQ Q. This is just because I didn't prove this result, but it's true. So P sub P, so each of the P's are projective. Tensor product is exact with projectives. So the result is that exact functors commute with homology. You have to prove that. It's not that bad, but you need to use a weird trick that I did not explain, so I'm not going to explain this, but it is true. So you can commute the functors around. And so, okay, what is HQ of Q? Well, Q is an exact sequence, so it's mostly zero, except, the way we've done this is, so what I mean by Q is, Q bullet is the part before mapping into B. So if you look at the complex, it'll stop at Q0 and then go into zero. So that part is not exact. And the homology there is going to be B. You can check that. So then you'll get this spectral sequence. 1E2 PQ. This thing is mostly zero. And then for Q equals 0, you get the horizontal homology at P of P tensor B, which is just L sub P of tensor B on A. Okay. Similar, you get another one, again, commuting an exact functor with homology. You get this. And then it'll be HV at P of A tensor Q, which is just LQ of A tensor dash on B. And this is Q equals 0, otherwise for the other one. Okay. So this one only has, so what I mean, so the first spectral sequence collapses. This one also collapses, right? Because there's only the Q equals 0. There's only the Q equals 0 rows in each of these. So this means that HP, the P homology of the total complex of P tensor Q is just LP dash tensor B on A. And the second spectral sequence also has this, but then, this is just, so this also isomorphic to LQ A tensor dash on B. But that's happy face. Great. That's the isomorphism. Nice. So that's fun. Okay. How am I on time? That doesn't help me. It's 4:22. Okay. So in the past, we had spoken about forming resolutions of some kind of objects in abelian categories. And you may wonder, can I form resolutions of complexes? Because after all, complexes form an abelian category. So, we should be able to speak about, there are things like projective objects in the category of chain complexes and injective objects. And so you can talk about exactness, blah, blah, blah. All the things we have, we have them. So we can talk about resolutions of chain complexes. And so what are they? So I will talk about what are these so-called Cartan-Eilenberg resolutions, which I'm pretty sure they should coincide with if we had, traced through the official definitions of resolutions of objects. You have to do a bit of work, right? Like what is a projective object in the category of complexes? You have to, actually find all these things, but it should coincide with what I'm about to say. So let's start with maybe in category A with enough projectives. Oh, that's weird. Okay. So A has enough projectives, and so then I can start with a projective, or sorry, I want to say projective resolution again and again, but they say right and left. So I left Cartan-Eilenberg resolution, P bullet of a complex. So here's a chain complex. Complex A bullet is an upper half plane double complex. So here that means PQ is equal to 0 if Q is less than 0. And these are made of projective objects. And there's also a chain map that goes P bullet 0 into A bullet. So just like before, but now we have to adapt this for the complexes, so that looks like this, and such that for every P, we have two things. One, the columns themselves. So that is, you fix a P and you get a column. Column are projective resolutions. And then also, if you take horizontal co-boundaries and if you take horizontal boundaries and horizontal homologies, you still get projective resolutions. So taking boundaries, so horizontal boundaries and homology, give still projective resolutions. And resolutions of what? That is resolutions of the boundaries of A and the homology of A. So you'll get something like BP. So at the very last stage, you'll get something like this. So this epsilon map or whatever. So this going from BP PDH into BP A. If you plug in that as well, and you look at the columns made of these BPs or whatever, you will still get a projective resolution. And same here with H, so on and so forth. And then there's also the dual thing for injectives, or there's like the injective resolution version of this. So we need injectives, and then we get a right. You put right here. So a lot of flipping things around. I bullet of a cochain complex, the upper bullet, and then you put IPQ equal to 0 if Q less than 0 of injective objects, and a chain map I upper bullet 0. It should be A into this, or B into that. And then such that for every P, you still get injective resolutions at each column, and then You can take co-boundaries, co-homology. So you can put all these things here and it would work out the same way. So, okay, fine. It's actually true that the having just the boundaries and the homology be projective resolutions also gets you that cycles also constitute. So the horizontal cycles constitute projective resolutions as well. Okay. And just like before, every object has a resolution. So now similarly, every complex has a Cartan-Eilenberg resolution. So every complex has a Cartan-Eilenberg resolution as expected. Why should this be true? This is true due to something called the horseshoe lemma, which maybe I shouldn't discuss, but maybe I'll say it in words. The point is, in the horseshoe lemma, you start with a short exact sequence of complexes, a short exact sequence of objects, and then you have projected resolutions of the first and the third objects in this, and you want to form a projected resolution of the thing in the middle. There's a way to do this. That is the content of the horseshoe lemma. And so you use that to cook up very carefully a Cartan-Eilenberg resolution. So why the special ingredient is the horseshoe lemma. So read about that. That's good. So then you might ask, like, now that we have these resolutions, is there like a corresponding like hyper or some, okay, I spoiled the name already, but you get these hyper derived functors. So you can talk about hyper cohomology and hyper homology and hyper tor, hyper ext, which I know nothing about, but it's very similar, all very formal. But I'm sure there are a lot of applications, but Weibull doesn't get into so much of it. But I mean, there was some talk, but I didn't want to focus on that. I just want to show that you can do a similar thing. And yeah, maybe I'll just write down the definition of the hyperderived functor. So if I start with f from A to B, these are abelian categories. So if I start with, say, a right exact functor, and let's say A has enough projectives, then if I start with an object or a complex A, maybe I should not put the bullet down. If A is a chain complex, and P into A is a Cartan-Eilenberg resolution of A, then we can form these hyperderived functors of F. So then they're written with this blackboard bold L, which is a fun letter. LIF on A. So right. So notice here that the thing that I put into this derived functor is a complex. So it is really the analog of, I mean, I think this is just pretty much just the derived functor, but in the situation where our abelian category is just the category of complexes, but we look at the functor we get if we upgrade f from A to B to f from complexes on A to complexes on B. But don't take my word on this. There may be some subtleties going on. Maybe these don't exactly agree somewhere, but spiritually, maybe this is what we might think. Okay, so then this hyperderived functor is just the homology of the total complex of f applied to p. So, okay. And so this is where the spectral sequences come in, because now I have the homology of a total complex, and so there's a device to calculate these things. There are spectral sequences that converge to this. And as expected, maybe these should be independent. So independent of the resolution P, and there's also some kind of long exact sequence in homology for these. So there's some version of long exact sequence, but we need A to be bounded below complex. For some technical reasons. Okay, and then there's similarly the ones for the right hyperderived functor. So if I just put left exact here, and injectives here, then I need injector resolution. So here, if B is a cochain complex and B into I is a resolution, then we get R upper I F on B is the cohomology of the total complex of Fi. Okay, great. Okay, so I should probably say something about what the spectral sequences are that converge to these. Time for 35, good. So the spectral sequences that converge to these hyperderived functors complexes. So here we need our complexes to be bounded below, just for technical reasons. Okay, and so what I'm going to write down is actually a result. There is something you need to check. You need to, again, commute a functor with homology in some particular way. It's not that bad. I've actually written up the details in a note somewhere, which I will talk more about later today. But that detail is interesting. But okay. So here, the first one is, well, for the left hyperderived functor, you should have the homological spectral sequences. So these look like these. So this is HP, LQ, F on A, and that'll converge to LP plus Q, F on A. And similarly, the second homological spectral sequence converging to the same thing is this. It's LPF on HQ of A. Okay. Similarly for the cohomological ones, or the right hyperderived functors. Oops. This first one is very similar. You just flip everything around. HP, RQ, F on A. And that converges to RP plus Q, FB. And then the second one is similar. RPF, HQ, Yeah, great. So yeah, all of this again is still coming from just the same theme of just finding the homology of a total complex, except here it's just sort of specialized to the ones that you get from the when you apply the functor to the Cartan-Eilenberg resolution. Fine.
Can I ask a question?
Yes.
So on the left hand side on each of these like spectral sequence, I see like the LQ is not bold, so
Right. So
just
here
a
this is
formula.
ordinary derived functor. Yeah.
Right, but the A is a complex, right?
Right.
So what is f of A?
Right. So here I mean you apply the derived functor pointwise to the complex and to all the maps in A. So this becomes a new. Well, how should I flip it around? This thing is a complex in the end, and then you can take homology of that complex. Yeah. Does this make sense?
Yeah.
Yeah. So this is a complex. Yeah. Good. Yeah, always type checking is good. Thank you. Okay. So here's a nice theorem to finish our talk on our whole discussion of spectral sequences with. And maybe it's nice just because of the application to algebraic geometry, I guess. Okay. So here's the setup. Let A, B, and C be abelian categories. Oops. Such that, oops, A and B have enough injectives. And there are left exact functors. So there are left exact functors. So I'll just draw the picture here. So there's one from A to B. Let's just call it G. So there's G from, and then I won't write the signatures. I'll just draw the picture. So F from B to C. There's another functor that way, and then we can also look at the composite, which is FG. So I have left exact functors. So this is the picture that I have, and I'll copy this for the next page. Okay, so this is the setup. And then the actual theorem, which is, they call this the Grothendieck spectral sequence. So, you know, if it has his name on it, it must be very important. Grothendieck spectral sequence. So now I assume if G sends injective objects to F acyclic objects. Remember, F acyclic just means that the higher derived functors of F vanish on that object. Then, so okay, objects. Okay, here. So in A to objects in B, right? Just to be sure. Then there is a convergent, spectral. So really it's a first quadrant spectral sequence for each A in A. And what is it? It's this one. It's given by RPF, then RQG, and this will converge to RP plus Q of FG. So you derive the composition you apply to A. So if you ever wanted to calculate the derived functor of a composition of functors, you could get pretty close by just knowing how to derive each of the functors individually. Oh, and this should be an A here. Oops. Yeah. Right. Good. So that's the result. There's actually a little bit more, but I'm not gonna talk about that. You can see it in Weibull. So, okay, here's the outline of the proof. So you start with an injective resolution of A. So A into I. Apply G to I to get the complex oops, GI in B, right? And then form the Cartan-Eilenberg resolution of GI and obtain the hyperderive functors on the GI. So R and F GI. So there are two spectral sequences converging to this RNF GI. So first, there is one E2PQ, which is, right, this is HP RQF on GI. This converges to RP plus Q of F on GI. But so for each P, so GI on P is F acyclic. So all of these RQF GIs, well, most of them are zero. So RQF on GIP is equal to 0 for Q equal to 0. So the spectral sequence collapses to yield what? So that's, oops, it's RPF GI. So here, now I'm taking Q equals 0 in the right-hand side here. So Q equals 0 up here. This thing is isomorphic to each of the, it is what the nodes are when you collapse, right? So it's just this nodes, HP of FG applied to I. And by definition, this is just the right derived functor of FG on A. Okay. But in the other spectral sequence, what do we get? But we get, okay, so 2E2 PQ. This thing was RPF. Then there's HQ of GI, right? This converges to, well, it converges to this thing because this thing is this, the homology or cohomology. But then maybe I'll simplify this. This is by definition RQG on I. Maybe I'll write it like, or on A, sorry. So that's the proof, right? You get this. Nice. Okay. So then to close, maybe I'll say a remark about algebraic geometry and sheaf cohomology. So I'll just say sheaf cohomology. So let's let f from x to y be continuous. Then I can look at, oh dear, someone is calling me. That's not good. Okay. So on sheaves, there are these functions. So on sheaves, on x, I can look at these following functors. I can look at the push forward and the pullback, and these form an adjoint pair. So f star is a right right is right adjoint to pullback. So then what does this say? Because of this adjointness relationship, I might have made some remarks earlier saying these things, so good to see these return. That is to say that f, the push forward is left exact, and then also that the okay, something you can check is that since this thing is exact, actually, you can show that then the pullback actually it just preserves injective objects. Great. So we're in the situation of the Grothendieck spectral sequence, or sorry, not F inverse, I mean this one. Yeah. Right. So push forward is left exact. Push forward also preserves injective sheaves. And okay, there are enough injectives in the category of sheaves on X. Okay. Maybe there were more adjectives needed, but I don't remember seeing any. Okay. And then there's also global sections functors on sheaves on X and on Y, right? Denoted by this gamma, right? So then what is the result? For any sheaf F on X, we have, so applied the spectral sequence from earlier. That's equal to HP. So the sheaf cohomology is notated this way. You put the space in here first. Y, comma, so RQ F asterisk. This is the derived functor of push forward. You apply this to F. This thing converges to the sheaf cohomology in P plus Q of X, or of F on X. So that's the result. So for calculations in sheaf cohomology, this is pretty neat. So you could imagine that maybe F is a nice map, and so maybe the derived functor could be convenient. Maybe Y is nice. Something nice could happen, and this is somehow really important. And then, you could also consider a different situation. So since the global sections on the space Y is the same as doing, so it's the push forward of G for this map. So the point, you map Y into a 1-point space. So if you push forward that map, that's the same as the global sections functor. So you could instead consider just any any G. From Y to Z. And, you know, there's similar results in that, you know, so that's cool. So supposedly algebraic geometers use this a lot. I'm still learning all about this, so we'll see how useful it is for me, but you know, this is cool. Yeah, this is all I wanted to say about spectral sequences. So I guess I will see you all tomorrow and Friday. I want to say stuff about the derived category, but we'll see how much we can get to. I mean, the problem is I don't know all that much, so we'll see. Okay, see you all next time. I will stop recording.
Y'all wanna, I'm gonna, actually,